Hi everyone, welcome to today's GOCC. It's my pleasure to introduce to you Mary Claire from UC Davis. She will talk about a crystal-based approach to Thrall's problem, but before I hand over the stage to her, let me remind us of the community statement with the 3 guiding principles. We are all learning, everyone has something to contribute, and no one has all the answers. With that said, please also ask questions in the chat or unmute yourself to ask the question directly to the speaker. And please keep in mind that this talk is recorded. Without further ado, Mary Claire, the stage is yours.
Thank you. Hi, everyone. Thank you for coming. And thank you, organizers and Stefan, for inviting me and for putting this together every week. I think it's great. And I'm really excited to have the opportunity to talk with you all today about this crystal-based approach to Thrall's problem. So this is a project I'm working on currently with Anna Schilling, Joseph Pappy, John Erickson, David Knepp, and Regina Zhao. And we all happen to be at UC Davis, so that makes collaborating easy. And we'd like to thank Vic Reiner for suggesting this problem to Anna over the summer. The idea of linking up Thrall's problem with her crystal-based kind of forte and setup. So, oops, sorry. There goes the slide. So this project is very much still a work in progress. And so what I'd like to accomplish today is setting up Thrall's problem for you all, giving you the relevant representation theoretic background. And then I'll go into some of the known cases for Thrall's problem. And where we'll spend most of our time is in describing this crystal-based approach and our group's preliminary observations working with a particular vertex set. So let's get started with the rep theory. Throughout the talk, script B will be an alphabet of size M for us. T of V will be the tensor algebra of this alphabet. And L of V will be the free Lie algebra on V, which is the Lie subalgebra of the tensor algebra generated by the letters in V and then successive bracketings of the form A tensor B minus B tensor A. And living in our free Lie algebra, we have these degree pieces Ln of V, which look like if you took n brackets of the letters on V, you'd get words that look like this. So we want to consider our tensor algebra as a standard representation of GLMC. And what that means is that for a matrix X, we will have X act diagonally. Oh, a little feedback, I'm good though. So X will act diagonally on a k-fold simple tensor and treat each letter I like the ith standard basis vector. So this is our standard representation or regular representation, however we call it. Then it turns out that our free Lie algebra is an actually graded GLMC submodule with these degree pieces we were looking at on the previous slide. So now we will refer to Ln as our Lie modules. But we want to go a step further and define what are known as the higher Lie modules. And to do that, we will bring up the universal enveloping algebra of our free Lie algebra. And it turns out that this is isomorphic to our tensor algebra. And we only need this isomorphism as GLMC representations. So the reason we bring up the universal enveloping algebra is we want to use the Poincaré-Birkhoff-Witt basis for this space in order to decompose this representation into this direct sum of symmetric powers of symmetric algebras of our Lie modules. So the takeaway from this top line here is that we have this decomposition as a direct sum over all partitions lambda, where we're denoting lambda in this kind of multiplicity form. So mi tells us the number of parts of length I in our partition lambda. And so these pieces on the right-hand side are what we'll call the higher Lie modules associated to lambda, and we'll denote that L lambda of V. And one thing to note right at the start is that when lambda is a partition containing one part of size n, we just return our original Lie modules that we were looking at. So we'll drop that one or n to the 1 notation and just consider these as our Lie modules. So now that we've at least looked at what the higher Lie modules are, we can state Thrall's problem, which he gave in a paper in 1942, asking for a combinatorial description for the multiplicities AU or A mu of the irreducible GLMC representations in our higher Lie modules. So Thrall's problem at the end of the day is asking us for a multiplicity count given by a combinatorial description. We can restate Thrall's problem in terms of symmetric functions by considering the GL character of our higher Lie module associated to lambda and asking for its shear function expansion. Okay, so this is stating Thrall's problem. And again, what we'll be looking for is how to count this A mu that's showing up for us. So getting into some of the known cases, maybe the biggest category that's known is that Thrall's problem has been solved for the Lie modules, not all of the higher Lie modules, but the partitions containing one part of size n. So here's the setup to state this result. Let's let SYT sub n denote the set of standard Young tableau with n boxes. And we'll consider all of our tableau today in English notation. Then the descent set of a standard Young tableau consists of all the entries I such that I plus 1 appears in a row below I in the tableau. I'll show some pictures in a moment. I also want to define the major index for a tableau, which will be the sum over the descent set of T. So when n is equal to 3, here are all of the standard Young tableau of size 3. And I've computed the major index for each of these here for us. So we see in the first example, we're just looking at a tableau with a single row. So there's no descents appear in this tableau. So we pick up a 0 for the major index. Then in the second one, we have that 1 sits above 2. So 1 appears in the descent set and in the major index. Now we have 2 above 3, which will give us a 2 in the descent set and thus in the major index. And then finally in the column, we have 1 above 2 and then 2 above 3, which contributes the 1 and the 2. So the result by Kraskowitz and Wayman in 1985 proved that the character expansion of the Lie module in terms of shear functions, the multiplicities we pick up are counted by the number of standard Young tableau of shape mu with major index congruent to 1 mod n. So if we want to look up at our above example, we're considering computing the character for L3, and we're looking for all standard Young tableau with major index congruent to 1 mod 3. And that only happens with this tableau right here, this 132. And so the character for L3 will then just be S21, the shape of this partition. Okay. And here's the computation done out for n equals 4. We only have 2 standard Young tableau, one of shape 2, 1, 1, and the other of shape 3, 1, which have major index congruent to 1 mod 4. For fun, I've included a computation for n equals 5. Now we have 5 such standard Young tableau, but please don't worry about what these are, what the shear functions are that we get right now. I just wanted to get to n equals 6 because this is when we start picking up non-trivial multiplicity on our for our shear functions. So we see multiple shapes, 3, 2, 1, and 2, 2, 1, 1, and let's see, 4, 1, 1 as well. Yeah. Okay, so again, this Kraskowitz-Wayman result proves Thrall's problem for, or solves Thrall's problem for our Lie modules. And there's a way to simplify Thrall's problem for the higher Lie modules by using Littlewood-Richardson coefficients. So I'll describe that next. A brief recap on how the Littlewood-Richardson coefficients work is that they will tell us the multiplicity of the irreducible representation V gamma in the tensor product of 2 other irreducible representations, V mu with V nu. And these coefficients count the number of semi-standard Young tableau of shape gamma skew mu with content nu, such that the row word of these tableau is a reverse lattice word. But please don't worry about what this set is. The important takeaway is that these coefficients are counted by a combinatorial set. And so how we'll be able to use this with our higher Lie modules, if we look down here at the bottom of the slide, I've written out again what L lambda looks like. And the idea is if we can decompose each of these symmetric algebras of our higher Lie modules into irreducible representations, we can then go ahead and apply Littlewood-Richardson to finish out the problem for us. So we can refocus Thrall's problem to specifically target partitions that are rectangular shaped. So this would be a partition having B parts of size A, this LAB. Okay, so that's our Littlewood-Richardson simplification. I have one more slide summarizing some other partial results. So when lambda is just a single column, then we know that the character of this higher-Lie module is equal to the shear function Sn. And when lambda contains two columns of the same length, then we also have a combinatorial description for the multiplicities of our shear functions here. Then I'll bring up two other results that are more general. And I also do want to mention that a lot of work's been done on Thrall's problem and in studying the higher-Lie modules and the free Lie algebra and so on. So for example, Sundaram, who I won't mention explicitly on the slides, has contributed a lot to this problem. But a big result was by Shocker in 2003, who gave a formula for the multiplicity of the irreducible V mu in our rectangular higher-Lie modules. However, this formula, I suppose, is not considered the combinatorial description that we're after, since it involves divisions and subtractions in general. So there's a Mobius function going on in the formula, and so Thrall's problem still remains open in general. And I wanted to bring up another group or pair who's working on this problem, so Albach and Swanson. And their current techniques involve using the cyclic sieving phenomenon so far in their proofs for known results. And they've set up a paradigm that will push Thrall's problem through in general once they find a certain statistic that they're looking for. But their work's been kind of interesting as well. Okay, I kind of blasted through this background a little bit just to get to the crystal-based approach where I want to spend most of our time. But I'll pause for a second if anyone wants to ask any questions about the background here. Okay, we can also circle back at the end of the talk. So getting into the crystals, what are crystals? Crystals are really lovely combinatorial objects that encode representation theoretic information in them. They were developed by Kashiwara in the 90s. Also Lustig and Littleman as well contributed. A lot of people pitched in. So on the surface, crystal graphs are directed graphs with labeled edges. So we have arrows directing our graph, and they're labeled with these 1s and 2s for this example on the left. And the edges of our crystal graph come from what are known as the crystal operators EI and FI. The FIs move us from the base of the arrow to the head of the arrow, and the EI sends us right back. So really we could draw the graph only knowing the FI operators. So for example, this top element up here, 2, 1, 1, has an edge labeled 1 connecting it to 2, 1, 2, which means that F1 applied to this vector results in this vector 2, 1, 2. Additionally, each vertex in our graph has a weight corresponding to it. And for all the crystals we'll look at today, the weight of our elements will count the number of 1s, the number of 2s, the number of 3s, and so on. So this top element up here has weight 2, 1, 0, since there are 2 1s and 1, 2. Another important piece of information is that each connected component in our crystal has a unique highest weight element, where a highest weight element is a vertex that has no arrows coming into it. So the example here, our highest weight element is 2, 1, 1 with highest weight 2, 1, 0. And this structure also satisfies additional conditions that I'm not getting into the details of. If anyone's interested, the textbook by Bump and Schilling, Crystal Bases, has a lot of great setup for the combinatorial definition of crystals and what we can use them for. Okay, so how do crystals tie into representations of GLMC? But it turns out that a specific type A sub m-1 crystals are in correspondence with the representations of GLMC. So the example crystal we have on the left, we will denote as B210, which is signaling out that highest weight that we have in our crystal. And this component here, this graph is in correspondence with the irreducible GLMC representation, also with highest weight 210. And this correspondence buys us a couple of pieces of information. One is that the size of the vertex set of our crystal will be equal to the dimension of our representation. And there's also other compatibility among weight spaces and number of elements of certain weights. The big takeaway is that we can define what's known as a crystal character to be the sum over all the vertices in our crystal, the monomials to their weight vectors. And this will exactly agree with the character for our representation. So we've essentially encoded information about the weight spaces in our crystal graph. And now we can consider this combinatorial object instead of the esoteric Hierle module, perhaps. So in particular, for all partitions mu, we will have a connected component in a type A sub n-1 crystal whose highest weight element is of weight mu, and thus the crystal character for this crystal B mu will be the Schur function S mu. So this is what we get out of it. Okay, so now I want to look at a particular example of a crystal that we'll spend a lot of time with later. So this nth degree piece of the tensor algebra of B is in correspondence with what's known as a crystal on words of length n from alphabet V. And you may guess that this B tensor n its vertex set just consists of all words of length n from this alphabet V. So I'll tell you that the weights of this word, of a word, will be the number of ones, the number of twos, so on, up to the number of m's. And now I will describe how the crystal operators work through an example. So consider this really long word U, and we want to know what happens if we apply an F1 or an, let's focus on F1. If we want to apply F1 to U. So something that I didn't mention that's part of the additional structure on crystals is that I know if I want to apply F1 to a word, I want to change the weight of the resulting vector by removing an I and adding in an I plus 1. So going into defining the crystal operators, I know that this is how I want my weights to change as I apply F1, for example. So essentially, I want to look and figure out which one I can change to a 2, if any. And here's how we decide which number 1 that we can switch. Is we start by deleting all of the letters that are not 1 or 2. So we only have 3s that we will now ignore, and we take this subword. Now we label all of our 1s with closed parentheses and all of our 2s with open parentheses. And we look to see which 2s and 1s pair up to kind of cancel each other out and delete themselves. So the fact that we have a open and closed parenthesis here will discount this pair to 1. Then we have another open parenthesis and closed parenthesis that will get rid of that 2-1 pair. And then finally, we have another 2-1 pair over here. So once we ignore all the letters that are involved in this pairing, we're left with a word that has 1s all on the left and 2s all on the right. And then the way that we decide how to apply F1 is we will change the rightmost unpaired 1 to a 2. So that would be this one in the example. And then I can also easily describe the EIs after doing this pairing rule. We will change the leftmost unpaired 2 to a 1. And in this way, we can see how these definitions will kind of work as this partial inverses to each other, where if I apply F1 and then E1, I should end up back at my same vector, essentially. So ignoring the long word example, we can focus on the crystal component we had earlier. And if we just want to look at this top vector here, this 2, 1, 1, the reason why the outside 1 changes to a 2 after applying F1 is because we had a close or an open parenthesis, closed parenthesis. So these 2, 1 paired up. And that's why this middle one stays a 1 and the outside 1 became a 2. Okay, so this is our signature rule. Okay, so here's an explicit example of a crystal on words of length 3 of type A2. And again, I didn't make this clear before, but this subscript on A is telling us how many letters are in our alphabet. So the fact that we have a 2 here means we have 3 letters. So we're kind of off by 1 there. And I wanted to bring up this example, please don't worry about what all these vertices are. The point is that a crystal can have multiple connected components. And what's really important for us are what these highest weight elements are. And they tell us, or they kind of index our connected components. So let's zoom in on those. So as I mentioned, our crystal on words of length 3 is now decomposed into 4 connected components. And each of them is like isomorphic to our connected component of highest weight 3, 0, 0. Here we have 3 ones and no other letters. Then we have 2 components of highest weight 2, 1, 0. He's outside and middle one. And then 1 component that's just the single vertex that has weight 1, 1, 1. So those are connected components. And these are in correspondence with the representations and the decomposition of the 3rd degree piece of the tensor algebra V as such. And then the one last perspective to look at is if we wanted to compute the crystal character of our crystal on words of length 3, we could think about summing over all the words of length 3 with 3 letters and taking their weights and adding them all up. But a quicker way would be just all we need to do is look at the highest weight elements in our components, and that tells us the multiplicity of the Schur functions that we get. So see, we have 1 copy of S3, 2 copies of S21, and 1 copy of S111. Okay, so now we're ready to state the objective of the crystal base approach to Thrall's problem. So our goal is to define a type A sub m-1 crystal structure on a combinatorial basis for our higher Lie modules corresponding to rectangular partitions, and then classify the highest weight elements. So what this will accomplish for us is that each connected component of our crystal C that has highest weight mu will then be isomorphic to this B mu, and thus contribute the Schur function S mu to the crystal character. Then, since we selected an appropriate vertex set for our crystal, the character of our higher Lie module will be equal to the character of our crystal, and we will know the Schur expansion of the character of our crystal, where A mu, that multiplicity or that coefficient, is the number of highest weight elements of weight mu in the crystal. So this is the setup for our crystal base approach to Thrall's problem. And I also want to mention here that this paradigm for Schur positivity is not new. It's been used successfully in the past. Just one example would be Morson-Schilling results. I think the paper was published in 2016, proving or giving a combinatorial description for the Schur expansion of the Stanley symmetric functions. I believe that was what it was. And they use the same paradigm essentially. Okay. Are there any questions on the crystal base setup at all? Okay, so I then want to spend the rest of the talk discussing what we found using our, what we think is a good candidate for a combinatorial basis for our higher Lie modules. So let's get into setting up what that vertex set will be and then what we've noticed so far. So recall that we're working with this alphabet on M letters. And now I'll say that a word with letters from V is primitive if it is not a proper power of another word, which essentially means it's not, it cannot be written as a smaller word multiple times. So let's first look at our non-example, and we see 1, 2, 1, 2 is multiple copies of the smaller word 1, 2. However, 1, 2, 1, 3 is not, so we would have a primitive word over here. Then the set of all cyclic rotations of a primitive word is called the primitive necklace. So from our example above, we would take all of the words 1, 2, 1, 3, 2, 1, 3, 1, 1, 3, 1, 2, and 3, 1, 2, 1 to be our necklace. Another way to note whether or not a word is primitive is if the size of the necklace is equal to the length of the word. So if we tried to take the necklace of 1, 2, 1, 2, we would only have 2 distinct words in there. Okay, so we don't just want primitive necklaces, we want multi-sets of primitive necklaces. So we'll say such a multi-set is of type lambda if M contains mi necklaces of length I. So for example, if we consider the multi-set containing the necklace 1, 2, the necklace 1, 2, and the necklace 1, 2, 1, 3, this multi-set is of type lambda 2 squared 4. We can define the weight of a multi-set of primitive necklaces M to be, again, the number of 1s, the number of 2s, so on up to the number of M's. And we'll take this among all the necklaces in M. So we can define the monomial x to the M to be x to the weight vector of our multi-set. And with our example above, we see that we have 4 1s appearing among all our necklaces, 3 2s, and then 1 3. So we would get the monomial x1 to the 4th, x2 to the 3rd, and x3. Okay, and then for some more notation, let M sub lambda denote the set of multisets of primitive necklaces of type lambda. So for a little example here, if we have lambda just a partition of one part of size 3, then we're looking at multisets of primitive necklaces containing one necklace of length 3. So I've written out all of these, these multisets here. And so these are all the primitive words of length 3 on 3 letters. And I've written out the corresponding monomials below. And these monomials may look familiar, in particular if you're thinking about how many ways we can fill a certain semi-standard Young tableau with 1s, 2s, and 3s. So this will lead us, this observation may lead us to the next result here. So Gessel and Reitnauer in their 1993 paper gave, excuse me, the character expansion of our higherly modules as a sum over these monomials x to the m, where m is a multiset of primitive necklaces of type m. So for example, here is what we were looking at on the previous slide. All of our multisets of type 3 gave us these monomials x1 squared, x2, and so on. And this happens to be the Schur function s21 on 3 variables, or sorry, the Schur polynomial then. So, okay, we have this. So now this sum up here looks very promising to us in terms of, describing kind of the this weight correspondence between weight spaces in L lambda and weights of multisets of primitive necklaces. So if we can define a type A sub m-1 crystal structure on multisets of primitive necklaces which contain B necklaces of length A, that's all this notation here, then this result would, this right-hand side would essentially be the crystal character, and we would have that our crystal character is equal to the character of the higherly module that we're considering. So that's why these multisets of primitive necklaces are a strong candidate for a vertex set for our crystal. Okay, so now that we have a strong candidate, our next big step to make, or next big move, is to actually find the crystal operators that we want to define on multisets of primitive necklaces. So as I mentioned before, what we are looking for in our FI operator is to take an object, change one I to an I+1, and that's it. So if we want to define an FI operator on multisets of primitive necklaces, we will need to figure out which necklace to work with in the multiset, which seems kind of, like we'll have a lot of choices. We will also need to, then act on a necklace, and the necklace itself, is a conjugacy class of rotation. So there's a lot of options for which word we're maybe thinking about when we want to apply F2, like how we want to look at a necklace. We could choose maybe the lex smallest word or the lex greatest or something like that. But then the biggest hurdle maybe is ensuring that our image will then also be primitive, because we're requiring that our necklaces are primitive words. So if we looked at the necklace 1, 2, 1, 3 and said we wanted to treat this necklace like a word of length 4 and have F2 act as it does on words of length 4 in that crystal, then our parentheses rule would have a closed parenthesis under the 2 and an open under the 3, and would change this 2 then. Since there's no pairing, we would be able to change this 2 to a 3, but however, we no longer have a primitive word. So looking out for like sneaky cases like this became a little bit of a nightmare, and finding all of them for our group, even with small n. So all of this setup was to say that we faced a couple of challenges while trying to directly define the crystal operators on this particular vertex set. So we switched course and instead decided to use, decided to start looking at a weight preserving bijection between our vertex set, multisets of primitive necklaces, and an existing vertex set for a type A sub m-1 crystal. And in using this, we can maybe try to like overlay our vertex set onto an existing crystal and kind of, inherit that crystal structure in order to get our result that we're looking for. And the bijection that we're using is Gessel's necklace bijection to associate a word of length n to a multi-set of primitive necklaces with n letters. And this is where we'll turn to next. Okay, so I'd like to describe Gessel's necklace bijection, and I'll just do this with an example here. So we'll start with a word, and our word will be 2, 1, 1, 3, 2, 3, 1, 2. And our first step is to find the standardization permutation of this word. And the way we do that is we first look at where our ones, the leftmost one that we have in our word, and we'll label that one with a 1, the next one with a 2, and the third one with a 3. And then we want to repeat the process with the 2s, and we'll have to go back to the start of the word and we'll pick up where we left off. So label our first 2 with a 4, our second 2 with a 5, and our third 2 with a 3. And then repeat again for the 3s to pick up a 7 and an 8. And what we end up with is a permutation written in one line or window notation that tells us the standardization of our word. The next step in the bijection is to compute the inverse of the standardization permutation and expand in cycle notation. Then we'll use these disjoint cycles to form primitive necklaces. So we will send our a cycle to the necklace with the corresponding indices involved. So what I mean by that is that the cycle 1, 2, 3, 7, 4 will be sent to the necklace with the first letter, which is a 2, the second letter, which is a 1, the third letter, which is a 3, then the 7th letter, which is a 1, and then the 4th letter, which is a 3. So that's how we go from a cycle to a primitive necklace. It takes proof to ensure that we do get a primitive necklace out of this. So then at the end of the day, we will have our original word mapping to this multi-set of primitive necklaces. Okay, and we'll return to this slide in a second. Just for fun, I've included the inverse map because I think it's a really neat magic trick that of course works out. So given a multi-set of primitive necklaces, here's how we will recover the original word. We will start by writing out each word in all of the necklaces and then order them all, increasing with infinite lexicographic order in a right justified tableau. So what I mean by that is we'll write out all of the words that come from our necklaces and then order them as I mentioned. And then the magic happens by just reading off the rightmost column, and that returns our original word. So this is a cool proof. It's just a little technical. But it fits in a couple of pages in it's included in the Gessel right now, our 1993 paper. Okay, but going back to our forward direction for a second, what I want to point out about what's great with this bijection is that we see that the weight of the word is equal to the weight of the multi-set of primitive necklaces that we have. We didn't change any of the letters, we just rearranged them. So we have a weight preserving bijection, and we also have that the type of our multi-set by construction is equal to the cycle type of our standardization permutation. So we had a cycle of length 5, 1, and 2, and we end up with the necklaces of length 5, 1, and 2 as well. So we're also preserving cycle type. Okay, and so now we're ready to look back and see how we can use this with our existing crystalline words of length 3. So recall, here's our Gessel. Right now, our result that our character for our higher Lie module corresponding to lambda could be written out as x to the m, where m is a multi-set of primitive necklaces of type lambda. But now we can use the Gessel necklace bijection to instead think of this as the sum over all words of length n, whose standardization permutation is of type lambda as well. So the slide is about to get a little busy, but what I want to emphasize before it does is that we can return to looking at our crystalline words of length 3 and highlight or group together words that have the same cycle type for their standardization permutation. So that's what all the highlighted parts here mean. So let's first look at this, the words highlighted in gray. So we can see just by kind of scanning this crystal component that these words are always weakly increasing. And what that means in terms of our standardization permutation is that, we label our first letter with a 1, our second with a 2, and our third with a 3. This gives us the permutation, the identity permutation back. So the cycle type corresponding to this gray piece here is 1 cubed. Okay, now if we go and kind of run through our Gessel-Reutenauer result, so if we want to ask what the character of L1 cubed is, then we're asking for the sum over all words with this standardization permutation of cycle type 1 cubed, but that happens to be all of the words in our crystal component. So in the case when lambda is 1 cubed, we are getting the crystal character for B300. So this highest weight of this crystal component was 300. And we've looked at this before, that will be equal to the Schur function S3. And we also saw in our partial results at the start that we know that the character for our higher Lie modules that are just a single column is precisely Sn. So we've agreed in terms of the partial solutions. So however, we can't play this crystal character trick with the other components because we see that the yellow pieces are not lying in their same crystal component. They're kind of switched around with the blues. So we can't use a crystal character argument to understand the Schur expansion of the, I suppose, of the words with this cycle type, say for the yellow cycle type 3. So here's the change that we would like to make in the existing crystal on words of length 3 in order to be able to use our crystal theory. So we want to move our yellow pieces together and our blue pieces together. So we'd want to define these, stitching operators, which essentially look like redefining how F1 and F2 act on just these specific vertices in order to disconnect the existing crystal and move this component over. So this is our aim at the moment, is to figure out how we can define these stitching operators for general N. And here's been kind of our steps to going about this. We start off by understanding what these highlighted pieces mean. They're disjoint right now, but how can we think of them individually? Then we'll want to think about how we can start to piece these things together so that we still maintain a crystal structure, and then, explicitly defining what the stitching operators will be. So for the rest of the time, I'll be able to describe, we can describe pretty well what these individual pieces, these induced subgraphs, look like. And so let's start by just focusing on the yellow piece for now. So, and what we want to do is figure out what their actual standardization permutation is. So we can look at the highest weight element 211 and note that we will get the word 312. That is our standardization permutation for this element. And that also happens to be the standardization permutation for this element. And of course, this word that is actually 312, and then also our bottom element. So the claim or observation is that highlighted pieces all contain the same standardization permutation. All of those words do. And in fact, every word with that standardization permutation lies in this connected component. So that's what we'll be able to prove in general, and then state some more observations. Okay, so now let's fix some permutation pi, and we will specify that pi has L substrings of increasing consecutive numbers of lengths mu1 up to mu L. So this will be a composition of n. And here's an example of what I mean by increasing consecutive numbers. So if we take pi to be this permutation here, I want to start by finding where 1 is in pi. If 2 is to the right of 1, I keep 2 in my substring. And then since 3 is not to the right of 2, I need to restart a new substring in order to pick up 3. So then 4 is to the right of 3, so I take 4. 5 is to the right of 4, so I take 5. And then I've reached the end of my words, so I need to stop my substring. So I'd circle back and pick up 6 as my third substring. Okay. So the proposition is that induced subgraphs of words with the same standardization permutation in the crystal on words of length n is connected. So let's give this vertex set the name st_pi. Then a word has standardization permutation pi if and only if this word contains exactly L weakly increasing substrings S1 up to SL, where these substrings lie in the exact same positions as those in pi. And this just comes from, kind of staring at the definition of standardization in these substrings for a bit. So here's just an example of a word that lies in this st_pi for the pi above. And I've highlighted here the increasing substrings and see how they appear in exactly the same positions. So if we wanted to compute the standardization permutation for this word, we start with 1, then we can pick up 2, and then we'll need to head back to the start for 3, 4, 5, and then 6. And that was precisely this pi that we had up above. Okay, I also want to single out a special element in that has standardization permutation equal to pi, and that will be the word that has only i's in the ith substring. So in our first substring, we only have 1s. In our second substring, we only have 2s, and then in our third substring, we have the 3. Okay. So suppose U has standardization permutation pi, but it's true that all letters K must appear in the same substring. This is from the definition. Also, if both the letters K and K plus 1, they both appear in the substring SI, then all of the Ks necessarily must be to the left of all of the letter K plus 1s. Again, this is because if any K plus 1 was on the left of a K, then we would need to restart our substring. And what this positioning of these Ks and K plus 1s gets us is that if we wanted to apply our signature bracketing rule to this word U and look at the K pairings, so looking at Ks and K plus 1s, labeling the Ks with closed parentheses and the K plus 1s with open parentheses, we would end up having no cancellations happening. We just have a word with Ks and then K plus 1s. And so our raising operator EK is allowed to change the leftmost K plus 1 to a K. So here now is an algorithm from getting to any word U up to the word VPi. So we can first make all of the substrings in U constant substrings. So I'll first change this 2 in the first substring to a 1 by applying an E1. Then I'll change this 4 in the this 4 in the second substring to a 3. And now I have constant substrings in these positions. And then next what we can do is change all of the substrings. Like the first substring we can make have all 1s, the second substring all 2s, and so on until we reach this VPi. So since our first substring already was at all 1s in this last step, we could move to the second substring, apply E2 3 times in order to drop all of our 3s to 2s, and so on and so forth. So here's this algorithm worked out in a example picture here. So all of the pink highlighted words have the standardization 2, 3, 4, 1 in them. And if we start down here at this word 3, 3, 4, 2, actually, first thing to note is where the substrings lie, right? So actually, let's go back up here to our standardization. So we see that we have our first substring just has the letter 1 in it in this position. And then we're weakly increasing after that. So we have, this is our second substring. So the 3 letters here. So, okay, back down to this word. Our first step in our algorithm is to make all of the substrings constant. So we want to change this 4 to a 3. We can do that by applying an E3. Now we have constant substrings. We can go ahead and change that first substring containing that 2 to a 1 by applying E1. And then we'll apply E2 3 times in order to reach our highest weight element of standardization permutation pi that we're looking at here. Okay, here's the proposition again. We now know that words with the same standardization permutation form a connected induced subgraph in our crystal on words. And as a corollary, we've also identified the highest weight element among them to be this v pi. And v pi has weight exactly giving the lengths of the increasing consecutive substrings in the permutation pi. Okay, so we can actually form a really cool correspondence between this composition here and the descent set of pi inverse. So let me define the descent set of pi inverse and indicate this correspondence. So the descent set of pi inverse are all elements j such that pi inverse of j is greater than pi inverse of j plus 1. So these precisely look like in our window notation, reading from left to right when we end up taking like a down step, kind of, if you want to think of it that way. So then the claim or observation is that the descent set of pi inverse is in fact equal to the set mu1 and then mu1 plus mu2 and so on up to mu1 plus up to mu l minus 1. And the proof I've included on a bonus slide if people want to see it, but it's a quick result just expanding out the definitions. And actually it appears kind of like as a side remark in the first few pages of Stanley's Enumerative Combinatorics Volume 1. So this is just kind of a fact to have picked up maybe somewhere. Okay, so we have that the weight of our highest weight vertex with standardization permutation pi is in this correspondence with the descent set of pi inverse. And we can actually, continue to say things about elements with standardization pi. So suppose that U has this weight gamma 1 up to gamma m. Then by this correspondence of how compositions can relate to sets, we would have our weight mu, our weight U, weight of U in correspondence with this set, the sums of all of our gammas. And it turns out that the descent set of pi is necessarily a subset of this set that we have here. And the reason why is because, remember, all of the letters K must appear in one substring in our word U. And so if we have, ones, twos, and threes lying in the first substring of U, then gamma 1 plus gamma 2 plus gamma 3 will look like mu1 that fills out the entire length of our first substring. So that's how we end up picking up the descent set of pi inverse as a subset of this CU. Okay, and then from all of these observations, we have this proposition that actually appears as a lemma in the Gessel right now paper, which is that if we sum over all words with the same standardization permutation and take their monomials, then this is equal to the following sum of monomials. So xi1 up to xin, where our indices are weakly increasing and they're capped at the letter m. And we require a strict increase in the indices when j is contained in the descent set of pi inverse. And this is precisely the definition of Gessel's fundamental quasisymmetric function corresponding to the descent set of pi inverse. So we can look at kind of a brief proof sketch for why this is true. So for each word with standardization permutation pi, I claim that each word in this set has a unique weight. And the reason why is if I hand you the weight and I tell you the standardization permutation, you can then write out what the word is. So the word's completely determined by those two pieces of information. That tells us that the monomial x to the weight of U appears exactly once on the left-hand side. Okay, so now let CU be the set corresponding to the weight of U. Then there will be, a couple of monomials on the right-hand side that have, strict increase in their indices exactly when K is in the set CU. But there will only appear one that has exactly the same content as U. So what I mean by that is we can consider the monomial x1 times x2 squared. So that is that strict increase after the first indice. But so does x2, x3 squared. But the content there is different. We either have content 1, 1, and 2, 2s, or we have 1, 2, and 2, 3s. So that's what I mean by exactly the same content. So this is just a rough sketch of why this proposition would end up being true. The takeaway for us is that words with the same standardization permutation contribute Gessel's fundamental quasisymmetric function corresponding to the descent set of pi inverse to the crystal character of crystal on words of length n. So this is kind of a way if we wanted to break up what the crystal character looks like in terms of Gessel's fundamental quasisymmetric functions. Okay, I also want to mention here that these realizations have also been made before. So like, I mean, I believe Heyman and Asaf were separately or maybe together. They've studied this, and Asaf's dual equivalence graphs look a lot at grouping together, you know, kind of, you could think of them as crystal elements into the pieces that contribute a Gessel quasisymmetric function to them. Additionally, in February, a paper Florence Masgaripe, I'm sorry if I'm messing the name up, published an interesting paper on the archive that kind of goes into exactly this kind of crystal decomposition, looking at crystal on Tableau. And it just kind of summarizes also a lot of what I'm talking about here. So this work's out there on the archive if anyone's interested, not by me, but by others. Okay, but let's tie this back all these observations into our Thrall's problem and what we're trying to do. So right now in the crystal on words of length 3, we're looking at a picture like this, where words with the same standardization permutation cycle type do not appear in the same connected component. However, this blue piece here and this yellow piece here provide the same Gessel fundamental quasisymmetric function to the crystal character for B210 for that. So what we'd like to do is define these stitching operators that will move these components around, or these connected pieces rather, so that we group together words with the same cycle type for their standardization permutations. Oh, I'm sorry, I'm not seeing chat. Okay, thank you for sharing the paper there. Okay, so I'm now ready to just summarize what we've been discussing. So what our group is trying to do is pursue a type A sub n-1 crystal structure on multi-sets of primitive necklaces of type lambda, or equivalently on words of length n with standardization permutation cycle type lambda. Then once we have this crystal structure, we want to characterize the highest weight elements in order to count the multiplicity of S mu and the character expansion. So here's a long string of equalities that we've kind of collected throughout this talk. This first comes from the Gessel-Reitenauer result or statement in 93. And then here's the Gessel's necklace bijection, allowing for us to think in terms of words of length n. And here's us grouping together words with the same standardization permutation into a Gessel fundamental quasisymmetric function. And our end result, hopefully, is viewing this as a crystal character so that we can count A mu as our highest weight elements. The next steps for our group include analyzing what kind of choices we have for our stitching operators for words of small lengths. We've done 3, 4, and we're working on options for 5. We could also decide to shift our focus to specifically look at certain partitions or cycle types. So we could think of a single part, which would just be our Lie modules, and which has already been proven, but maybe if we get a crystal on that, we can extend that to the higher Lie modules somehow. Another option is to look at derangements. That was also suggested by Vic Reiner. And then another route to go, instead of focusing on all the stitching operators, is instead to define a dual equivalence graph on permutations with the same cycle type. And this would also be a route forward for Thrall's problem. Okay, thank you. That's my summary slide. So, are there any general questions?
Let's first thank our speaker. So, are there questions? Okay, then I guess I'll ask the first question. Can you already recover some of the known results?
With the crystal approach,
Yes.
only for the 3 and 4 we can recover what we had or what we have for the Lie modules essentially. So we did start focusing on that Kraskowitz and Wayman idea where we know precisely what that Schur expansion should look like. So yeah, we don't have anything for general N yet.
Okay, thank you. Are there other questions?
And the 2 to the b, I assume this is just Littlewood, right?
Oh, sorry, could you say again?
The 2 to the b formula, where you get the sum over all this lambda, where lambda has even entries or so.
Oh,
This
yes,
is
yeah.
the
So
symmetrics.
precisely. There's another statement of Thrall's problem in terms of plethism, and that's exactly how you get, so using the Littlewood plethism result, you get lambda is equal to 2 to the b, that Thrall's solution. Mm-hmm.
I guess this has been proved using crystals, has it?
Oh, it's possible, and I'm unfamiliar with it. If anyone else.
Sheila might know. Okay. Yeah.
No,
anyway,
actually, I don't know about a crystal proof, but I had a different question. If you can do 2 to the b, then you can do 2 to the b time and 1 to the something, right? By
right.
Littlewood-Richardson.
Littlewood-Richardson, precisely.
Can you see that in your crystals?
Oh, that's a good question. I would need to think more about that, but I think that would be an interesting perspective, because that would also apply to partitions with distinct parts. We can immediately apply Littlewood-Richardson using the Karskowitz-Wayman result as well.
Yeah, exactly.
Yeah, so thank you for that.
Are there more questions? Okay, if not, let's thank our speaker again for the very nice talk.
Thank you all. Really appreciate it.
Thank you. Very nice talk.
And
Yeah,
we
that
can
was
stop the
really
recording.
very interesting.